Hello everyone, it's Homer White back again with the first of a two-part video series on the third homework data analysis assignment. Following our usual pattern, the first video lecture will address the structure of the data analysis report itself and some of the new features pertaining to the fact that we're going to be doing a test. The video lecture will discuss any new features of R or R Markdown that were employed in the production of this report. So as for the report itself, it's an analysis of a little study done on repeatability of lizard sprinting speed. So I'm going to assign you the task of pulling this Word document up from where it is located in the RStudio Common Source folder, and then come back when you have read the thing through once. Alright, assuming that you've read it through once, it's a data analysis report, so it's going to have the usual four sections: introductions, methods, results, and conclusion and discussion. As a brief reminder from your reading of the paper, what we're analyzing here is some results from a journal article on the repeatability of locomotor performance in natural populations of canyon lizards. So what the authors did was to look to see if the sprinting speed of canyon lizards changes over what would be a fairly short part of their lifespan, just 1 year. If speeds change a great deal over the course of a short part of a lizard's lifetime, then using their speed as a measure for their adaptive fitness to their environment might cause difficulty in other biological studies. So we've got this research question: do canyon lizard sprinting speeds change on average in the period of 1 year? This is a question about the population as a whole, and we're going to try to answer it based on 34, presumably randomly selected, canyon lizards that we have in our study. Remember, each lizard had its sprinting speed measured at the beginning of 1 year, and then each lizard's speed was measured again at the end of that 1 year period, and we're interested in the differences. One unusual feature of this data frame, which may not occur to you at all in any assignment or project that you have in this class, but that will probably occur to you later on if you continue using statistics, is the way that the data frame is structured. We're used to having the two speeds come as two separate variables in the data frame, whereas in the lizard sprint data frame from the package ABD, the speeds all come in one column titled speed. What differentiates the initial speed from the speed 1 year later for each lizard is how the rows work. Every lizard here has an identifying number. There's a lizard number 1, a lizard number 2, all the way up to a lizard number 34, presumably at the bottom of this data frame. And because there's two measurements on each lizard, there are therefore two rows corresponding to each lizard. And what you have to learn from the study itself is that the first member of the two-row pair gives you the initial speed of the lizard, and the second member will give you the speed of that same lizard 1 year later. If we're interested in the difference of the speeds, this is going to be a fairly difficult data frame to work with. It would be nice to have the speeds lined up next to each other in separate columns so that we can subtract them easily to look at differences, rather than have the speeds recorded in this particular way. So in our methods section, we're going to actually talk to the reader about how we manipulate the data frame to create a new one that is in a format more suitable for the kind of analysis we're prepared to do at this point in our statistical careers. So this might be a time when you would want to talk to the reader about the R code that you use to do the data manipulation. We'll go into more details in the next video, but basically we create two new variables from the variables in the old data frame and stick those two variables together into a new data frame called lizards. And if you were to print out the first 6 lines of this new data frame, you'll see that it has a somewhat different structure. Each line now corresponds to one lizard and to everything we know about that one lizard. Lizard number 1 ran 1.43 meters per second at the beginning of the study and 1.37 meters per second 1 year later. Same for all the other lizards in the study. There would be 34 lines in this new data frame, lizards. The variable analysis, well, we take a look at the two variables, first speed and second speed. They're both numerical, and they're paired up in a certain way. In fact, what we have here is a repeated measures study. We measured each lizard twice. Generally, in a repeated measure study, you're going to be interested in the difference between the two measures. So we should construct a new variable, which we'll call speed diff, and it could be the first speed minus the second or the second speed minus the first. We chose to do the second speed minus the first and just told the reader that. And for extra convenience, we're going to add that new variable to the data frame lizards using this code here, which we'll explain later in the second video. Creating the speed differences on their own as a separate variable is a convenient thing if you want to study the speed differences using your descriptive statistics. We finish up our discussion of methods by talking about the inferential techniques we're going to use. We should make a test of significance. We'll also make a confidence interval as well. They always come along with our test of significance. So we'll make a 95% confidence interval for the parameter of interest. Notice here we've defined the parameter of interest up front in the methods section. That's fine to do. Our parameter mu d is the mean difference in speed for all canyon lizards in the population, not just for the 34 lizards in the study. After all, we know the mean difference in speed for the 34 lizards in our study. What's of interest is what's going on in the population. And we're interested in whether mu d is 0 or not. If it's 0, that means on average speeds don't change out there. And then perhaps measuring speed could be a good way of indicating fitness of a canyon lizard for its environment. When it comes to results, you do the usual thing. Divide your results into your descriptive results and your inferential results. And when you work with your descriptive results, try to provide both graphical and numerical results with some discussion of each as to how they pertain to your research question. For graphical results, we chose to make a density plot of speed diff, the differences in the speeds. Remember again that when you make a plot, it's a good idea to have labels for the axes when possible and to give units when possible. The speeds were in meters per second, so we give those units. Little discussion about the distribution of the speed differences that we see. It's unimodal, symmetric, approximately bell-shaped. And that's important when you think about safety checks for confidence intervals and tests of significance. But also, pertaining to the research question, the really important thing to notice here is that the speeds seem to center around a number that's fairly close to 0. So there's not much change in the speeds out there on average. We did notice when we looked at the rug for our density plot that there is one speed that seems to be a lot lower, one change in speeds that seems to be a lot lower than the others. We might wonder if that should be considered an outlier. So on the spur of the moment, we decide to make a box plot just to see what R thinks about that one speed, and it does indeed flag that speed as a possible outlier for consideration. We don't know of any reason why we should exclude that particular observation from the study. No particular reason to believe that there was a typo there or anything like that, or that this lizard isn't really a canyon lizard at all. We have no information about that from the original study, so we'll keep it in the data. For numerical descriptive results, we chose to do favestats again as usual, and since we're interested in what's going on typically, then we'll be looking at measures of center like median and mean. Both of them are fairly small, negative numbers, but fairly small, so speeds are going down on average in the sample, but not by a whole lot. Here's an interesting additional discussion looking at the percentage change in speed on average over the 1 year period. That's something that seems to make sense to do in this particular study. You may have no occasion to think about percentage changes in your particular assignment. As for the inferential results, you'll remember that t-test GC allows us to work with repeated measure studies and matched pair studies, and that indeed is the code that was run to produce the output that you see. All we've got to do here is set up hypotheses for the reader, and then we show the output. Apparently we've hidden the code. And don't forget, when you show a great deal of written output like this, you want to address each important aspect of the output in relation to your research question. So you're going to want to do things like address what's the standard error, what's that all about, what's that telling you. You're going to want to mention the confidence interval and interpret it. You're going to want to run through the basic steps of a test of significance, hitting each one of them in your discussion. You don't have to number out these steps in any formal way, but you do want to address each one. So remember, in a test of significance, step 1 is defining the parameter and stating hypotheses. Defining the parameter turned out to happen most naturally for us way back up in the methods section when we defined mu_d. The second part of that first step happened much later when we lined out our hypotheses here in the inferential results subsection. Step 2 was a safety check and a discussion of the test statistic. We're going to reserve the safety check for the final section of the report in discussion and conclusions. There is a brief mention of the test statistic, however, in the discussion right here. Step 3 was getting the p-value and interpreting it. Here we have the p-value, and here we have a good intuitive interpretation of it. Step 4 was making a decision about the null hypothesis. We're not going to reject it in this case. Step 5 is an overall conclusion, and we're going to do that in our final section of the report under discussion and conclusion. So all 5 of the steps of a test of significance actually got addressed, but not in some formal lined out way as if we were little school children, but rather as grown-ups talking to grown-ups in a way that's convenient and clear to the reader. In discussion and conclusion, we do have an overall conclusion to the effect that our data did not provide very strong evidence in this case that lizard speeds do change on average. There's also a little bit of talk about whether the change, if it's present at all, could be big enough to be important to biologists.